And in this lecture, we're going to be talking about I think a lot of people mentioned an interest in this, but this is talking about how we can understand Fry, the fast Reed-Solomon inclusion, I think is the if you expand that adjective, I think that's what it expands to. How it relates to the framework that we've been presenting previously. So around how we can understand it from a purely linear algebraic perspective, without much reference to polynomials or things like that. Unfortunately, at the end of the day, there are many tricks that Fry uses in order to kind of get a succinct proof scheme that do depend on these facts about polynomials, but they can be just essentially distended or carefully kind of pulled apart from the underlying protocol, which actually is completely independent of those tricks. But to get a practical protocol, you have to use some of these like slightly more advanced techniques, which give you a little bit more structure. Okay, but to do that, we have to discuss something which we only vaguely mentioned previously, which is vector subspaces, and specifically the structure of vector subspaces. So, okay, I'll get to that. But so this one will be distinguished from the past two talks. So in the first session, we went through mostly math. The second session, we went through a number of tools that we kind of appear a lot. In this session, we're actually going to go through a specific protocol, and we're going to introduce just the things required to kind of understand it at a high level. Unfortunately, it turns out I tried my best, but it's actually quite difficult still to come up with a fully contained set of slides that is accessible to everybody for how to understand Fry and a simple proof. So if you're interested in the actual proof of how all of this works, I would recommend going to the paper. I will skip through some small details around the exact mechanics of things around finite fields, which turns out to be required for this. But those are also in the paper. But here we'll understand at a very high level, not just at a very high level, actually at a much deeper level than I think many tutorials on it will go. But we will not understand it quite yet at the deep enough level to be able to prove its security just from the slides. So, but again, this should set you up very nicely to go read the paper and understand the structure of the argument and just be able to prove it. The proof is not particularly hard, and none of it is particularly difficult in a lot of ways, but it is involved. Like it does involve details that are important. Okay, so let's go through an overview of what we're going to go through today, and then we're going to rehash a little bit of vector subspaces, and then we're going to do two things, which is we're going to introduce kind of an exact version of Fry, I think is the best way I'm going to put it. And then we're going to see how we can generalize that slightly to kind of an inexact or sparse version of Fry that will actually is actually the true protocol itself. So that's the high level structure. The exact version should be easier to understand for a lot of kind of annoying mechanical reasons. But that'll give you a good high level structure to understand the actual general check and how it actually operates. But to do that, we have to talk about vector subspaces. So how these things are structured and why we care about them. Okay, so as I mentioned before, we've already studied kind of all the main tools necessary to understand this protocol and most of the major checks, right, that people kind of use in kind of as the basis of a lot of zero knowledge protocols. So these were both done partially via homework, one of which I have not released yet, but which I will hopefully soon, and also lecture. So now this lecture is actually doing something quite real with them. We're going to start with a bunch of little disparate tools like little hammers and nails and things like that, and actually put them together to build some tiny little structure that's hopefully useful to understanding kind of some of these more complicated protocols more broadly. So the main idea, as I mentioned before, will be to understand Fry, its construction, and kind of how one can think about it very naturally. How we begin with something that is, if you just look at the protocol itself, it feels very magical. But if you begin from kind of the linear algebraic perspective and you just slowly relax it to fit this general framework, it turns out that the notion of how one might perform this check arises actually quite naturally. It doesn't require kind of all of the individual pieces that come together for you to understand the high-level structure of the check. So unfortunately, because we're discussing a specific protocol, we're going to need some specific setup that is related intimately with the protocol itself. So unlike the previous tools that we've discussed that are very generic, here we're actually going to need a little bit more structure that is going to be, we're going to use only for this protocol rather than for kind of being able to say, hey, here's a thing that holds generically for a lot of things. And the main tool that we're going to use is the fact that a vector space or a vector subspace recursively decomposes. So in some sense, we can think of it as a notion of self-similarity. I'll discuss exactly what this means in this slides. But the point is we can think about a vector space as being composed of like two vector spaces, each of which are smaller. And smaller in some sense, that's very practical, such that if we want to verify something about the big vector space, we can verify a smaller fact that's easier to verify of the two smaller vector spaces, right? And if this decomposition happens to do so recursively, so in particular, if the big vector space decomposes into two smaller vector spaces, and those two smaller vector spaces decompose themselves into even smaller vector spaces, then you can just imagine applying this construction recursively. And if we get a constant amount of savings at each step, then at the end of the day, we get an exponential amount of savings by going down this tree, as opposed to kind of trying to verify the claim over the original space. Okay. So much in the similar way of the structure of the previous set of lectures, so the previous session, which is we start with the exact case and then move to the inexact case. We're going to do the same thing here. So we're going to start with some notion of a protocol that kind of looks like Phi, that in this exact case. And then we're going to relax it to the case where we don't care about something being exactly in a vector space, but we only care about being close to a certain vector space. Okay. So quickly, let's go over vector subspaces and let's actually talk about what it means to have structure. So what is a structure that we require out of these vector subspaces? And again, I'm actually staring at the chat this time as well, so please feel free to ask questions in the chat, and I'll try to answer them as I go. Okay, so let's start again with the subspace. So if you recall, a subspace, we're going to call it V here, is simply a set. And that set has the following property. If you take any two vectors from that set and you add them together, they are also in the set. And if you take any vector from the set, so from a subspace, and you scale it by any number, then that is also in the set itself. Okay, so we're going to have three subspaces here. So one of them is going to be V, and then V prime, and then V prime prime. And they're all going to be part of the same, and they're all subspaces of n-dimensional vectors. And we're going to say that V decomposes into the two vector subspaces if for every vector x that lies in this vector subspace, that vector actually equals the sum of two vectors, one of which is in V prime and one of which is in V prime prime. So parse this quite carefully, right? What we're saying is we take a vector in x, right? Or sorry, we take a vector x, which is in V, and then any vector that in that space, so any x, can be written as a sum of two vectors, one of which is in V prime and one of which is in V prime prime, right? And so ideally, if by some intuitive way, these vector spaces are smaller, right? And we'll say what smaller means in a second. But in some ways, if these things are smaller than the original vector space V, then we can kind of check something that is individually smaller, right? We check that Y is in V and Z is in V prime prime in order to check that X itself, which is some of those two vectors, belongs in the original space. And as a notion of notational convenience, we read that as capital V equals V prime plus V prime prime. So this is called the Minkowski sum of sets. I wouldn't worry too much about it. For now, just think of it as I've defined the notation such that the bottom thing is true if and only if the top thing is true. So V equals V prime plus V prime prime. If and only if, for every vector in V, we can write it as a sum of two vectors, one of which is in V prime and one of which is in V prime prime. So that'll be the definition of the notation. And that's called the Minkowski sum if you're interested. Okay. So the simplest example is the following. Okay, let V be the set of all two vectors. So these are vectors with two entries. That's pretty simple. Here's a simple way it decomposes. It decomposes into two subspaces, one of which is the set of all vectors whose first entry is non-zero. And then the second of which is the set of all vectors whose second entry is non-zero. Right? That's kind of a silly decomposition. All we're saying is, okay, like a vector with two elements decomposes in two vectors of one element each. Right? And then, of course, summing those gives you the set of all vectors of two elements. Okay. So that's a very simple example, but the point is, kind of at a high level, this has a structure, which is we take a thing, right, which is of, dimension 2, right, and we reduce it into the sum of two things that are dimension 1. That's the like high level idea. Okay, here's a more complicated example, which we're actually going to use throughout this, and it's going to sound really deep when I formulate it this way. The next slide will show you that it's actually really not that deep of a statement, but or at least it's not that complicated of a statement. It is a deep statement, but it's not that hard to understand. So, okay, so from before, if you remember from homework 1, we're going the space of Reed-Solomon code words V, which is defined as a set of polynomials of degree less than or equal to n-1. It's a vector of which you take that polynomial and you evaluate it at a bunch of fixed points. So these are called the evaluation points, and we call those alpha 1 through alpha n. That's a vector space, if you recall from homework 1. And so specifically, we're going to call that vector space capital V. And that vector space also itself has this kind of structure that decomposes very nicely. So, sorry, here's a lot of text in the page, and I apologize, but I'll give you a more clear description of what this means. But if we define the following two subspaces, so V prime is, again, the polynomial evaluations, except here's the following thing. The polynomial only has even powers. So it only has the powers, x to the 0, x squared, x to the 4th, x to the 6th, and so on and so forth. And the degree is less than or equal to n-1. Right? So the evaluations of those types of polynomials are going to be make a vector space V prime, and you should verify that it's a vector space. It's clear that it's a reasonable thing to talk about. It's just not clear that it's a vector space, so that'll be a homework exercise. And then we have a second vector space, which is the same thing. So the evaluation of a polynomial f over the same points, except that it only has the odd powers. So it only has the powers of x to the 1st, x to the 3rd, x to the 5th, and so on and so forth, all of degree less than or equal to n-1. Then in that case, the vector space V of all polynomials of degree less than or equal to n-1 evaluated on alpha 1 through alpha n is actually equal to the sum of the even powers of those polynomials less than or equal to n-1 and the odd powers of polynomials less than or equal to n-1. Okay, so take a second to kind of take this in. This is going to be a very important structure that we're going to use throughout. But at a high level, it's kind of not if it seems too complicated, it's not that hard of a statement, and we're going to see why in a second. So here's the idea. Let's let n be even, just for now. Okay. And of course, a polynomial evaluated at alpha, what is that? Well, that's the coefficients of a polynomial, which we're going to call x, right? And it's going to be the first coefficient times 1, plus the second coefficient times alpha, plus the third coefficient times alpha squared, plus so on and so forth until the last coefficient times alpha to the n-1. Okay. So if you can see, right, I have the following things are outlined here. X1 times 1, that can be written as x1 times alpha to the 0, right? And x3 times alpha squared can be written as another even term, right? So x to the 0 is an even power alpha to the 0 is an even power of alpha. Alpha squared is an even power of alpha, and so on and so forth. So those are the even powers of f, of some polynomial. And similarly, we can do the same thing with the odd powers, which are here in red, right? So we have x2 times alpha plus x4 times alpha cubed, and so on and so forth, all the way to the last entry. Okay. So in this sense, of course, a polynomial can be written as the sum of its even powers and the sum of its odd powers, right? And so we can rewrite it in the following way. Let's just rearrange the polynomial into two sections, one of which is the even powers and one of which is the odd powers. And of course, from here, right, that the first set of terms is exactly equivalent to the vector space V prime here that we have. And the second term is equal to the space V prime prime, right? So the point is, it's not a deep statement, or at least not a difficult statement, that you can take a polynomial and divide it into its even and odd powers and have something. And those even powers and those odd powers are themselves vector spaces that are reasonable to consider. Okay. So that's a notion of decomposition. We're going to talk about a notion of kind of recursive decomposition. I don't have a better term for this. So if anyone does, I'm happy to take it. But it's a term that's made up. Let's call it recursive decomposition, which is, okay. So the first observation for this is if we have a vector space V and some matrix T, which is consistent. So in particular, T is going to map n vectors into m vectors. And the vector space V is a vector space of n vectors. Okay, such that the idea is if we pick an element of V and multiply T by that element, then we get an m vector out. Okay. The following thing is also a vector space. T times every element of V aggregated into one set. Okay, and that's just what I defined here. So that's also a vector space. This is going to be a homework problem, but okay. And the idea is we're going to say a subspace recursively decomposes in the follow if it satisfies the following property. If there are matrices T1 and T2, both of the same dimensions, such that V equals T1 times a vector space V prime plus T2 times the same vector space V prime. And specifically, the point is that the vector space between, in front of T1 and T2 are actually identical. So they are the same vector space. This is the notion of the recursive decomposition that we're going to use. Okay. So here's this, it turns out the first example that we gave actually also satisfies this structure. And this is pretty easy to see. If you think about it, right, the vector space of all two vectors, right, is simply the same as saying you're free to multiply the 1, 0 vector by anything you want. And you're also free to multiply the 0, 1 vector by anything you want. And if you add those two things together, you get the set of all possible two vectors, right? Again, if you think about it, you can scale the first vector, which is 1, 0, by anything, right? That's what it means to do 1, 0 times f. So the set of all possible field elements. And then the second one says, okay, you can also scale a 0, 1 vector by anything, right? And then you can add those things together. And certainly that gives you any two vector that you want, right? Again, not a super deep statement, but it's an important one to parse, right? More broadly, if we have an even number of dimensions, right, we can actually generalize a statement. And it's kind of silly. What it says is, okay, any vector space that has 2 times n dimensions, right, or as an f2 to the n, let's say, actually, can be decomposed into the following two things. It can be decomposed into its first n entries and its second n entries, right? And so, of course, if I take any vector here, and I can take any vector here, and I can add those two things together, I, of course, recover the set of all 2 to the n, or 2 times n vectors. And not a super deep statement, but it's worth checking it carefully. So I would recommend taking a peek at the homework. Okay. So before, we gave an example around Reed-Solomon codes. Now there's a question. Okay, do these things also have recursive substructure? And the answer is yes. So we're going to start with only one of the subspaces. So we discussed two subspaces in the past, which is V prime and V prime prime, which were the even and odd powers respectively. We're going to see that we can actually write the set of odd powers as kind of some multiplication times the set of all even powered evaluations of the polynomials. Okay. So from before, we have the same vector space. The vector space is the original V is defined as a polynomial of degree less than or equal to n minus 1, evaluated at a bunch of points, alpha 1 through alpha n. And we have the set of kind of even powered polynomials of degree less than or equal to 1, evaluated from alpha 1 to alpha m. Okay. And what is surprising, and I'm going to leave this one as a homework exercise because it's kind of hard to, it's very easy to see once you sit down and write it out, but kind of hard to explain, is that it turns out that you can write V as the following sum, the set of even powers, right, plus a diagonal matrix whose elements are whose diagonal elements are the evaluation points, times the vector space itself again. So I'm going to leave that one as an exercise to the reader because it's hard to explain in words, but easy to explain when you sit down and write it. But if you don't believe me on this, recommend as a follow along exercise. If you would like to continue with the lecture, feel free to believe me on this, and you can prove it yourself in the homework. Okay. So with that, we actually have kind of all the structure we need to do the simplest possible thing, which is an exact subspace check. I'll say what that means in a second. But the point is, these spaces, specifically the set of Reed-Solomon codes, vector spaces of Reed-Solomon codes of degree less than or equal to n-1. But sorry, that's a mouthful, but the high-level idea is there. They have a lot of structure. So we want to exploit that structure in some way to essentially prove that something belongs in the big vector space by proving that it belongs to these smaller vector spaces, as I've discussed previously. Okay, so let's design a simple-ish protocol that does exactly that. So what's the idea? What is the check that we want to achieve? Well, we start with a vector x, and we would like to check that the vector x is in some vector space, capital V. And we're going to assume, of course, that this vector space, this vector space is known. We don't know if x is in this vector space, but the vector space itself is known. And we also know that it has this recursive substructure. So specifically, we know that it can be written down as the sum of two vector spaces, T1 times V prime and T2 times V prime. Okay, so it has this notion of recursive substructure where it's like the vector space V can be written in terms of these individual other vector spaces, V prime, some matrix times V prime. Okay, so what does it suffice to check? Well, all we have to do by definition is if V equals T1 V prime plus T2 V prime, then that means that every X can be written as the following, as T1 times a vector Y plus T2 times a vector Z when Y and Z belong to V prime, right? That's just the definition of this like kind of weird equality thing that we wrote up there. That's the definition that we said originally. And so now it suffices to check simply two things. First, we have to check, we are given some vector Y and Z that is claimed to be, the decomposition of X, right? So how do we think about that? Well, we have to check first that the equality is satisfied. So X actually does indeed equal T1 times Y plus T2 times Z. That's a reasonable thing to check. And so that's that equality. If that equality is satisfied, then we're good with the fact that X is at least equal to those things. And then the next question is, okay, but we also need to verify that indeed like Y and Z, each of them belong to this vector space V prime, right? Because if they don't, then we have said nothing about X, right? So those two things will imply that X is in V by our definition. So here is, at a high level, this already gives us some savings. So you could imagine, for example, that checking that, a thing in V takes about n squared time. If V prime is a dimension about half of V, which it should be, it needs to be at least that, right? Then we have the following property that we've already saved time, right? So we've taken a thing that scales, super linearly in the number of entries, and we've divided it into the sum of two smaller number of entries, right? And so if checking that we lie in a vector space V is super linear in the number of entries, and we can decompose it into two smaller versions of that, then we've saved a lot of time, right? Because super linear means that the sum of the two things is more expensive than checking of each of the individual elements. Okay. And so, of course, then we also have this nice property that if V prime itself decomposes further, so if V prime is also recursively decomposes into, T1 prime, V prime prime plus T2 prime, V prime prime, right? In other words, it decomposes in the same way that V does. Then we can apply the same procedure again to the individual entries. And, you can imagine that if this is true all the time, then you can continue kind of following this tree all the way down. Okay. So there's a question here, though. There's no randomness here, right? Like all we've done is we've given a deterministic claim, and we can just check it deterministically. That's not too surprising. So where does randomness actually come in? So from before, this is the same setup as we've had before, as we have a matrix G, which is some code, right? And in this case, G is going to have m rows and 2 columns. So it's a very kind of silly code, and it's going to have some distance d, whatever the distance is. So if you remember the vector subspace check from session 2, which that one we actually did prove, we know that in order to check the two elements, Y and Z, belong in V prime, it suffices to check that kind of this structured random linear combination of y and z themselves belong in V prime. So if this random linear combination of these two vectors belongs in V prime, then we know that actually the original two vectors belong in V prime as well, with high probability. It might not always be true, but it's generally going to be true. And so now we can replace the last step of the previous protocol, which is that y and z are in V prime. We can replace it with a single check for a single subspace, right? Which is, we're going to replace that last section with drawing a random number r from 1 to m, and then verifying that the random structured linear combination of y and z lies in V prime, right? And of course, because that implies that y and z are in V prime, right? And that, along with the equality check that you have that x equals t1y plus t2z also hold, then we know immediately that x must also have been in the original vector space. So just, it's worth thinking about, right? Why does this weird protocol imply that x is in V with probability less than, with error probability less than or equal to V? Sorry, here's the question by Mahmoud. Does having a check in a recursive decomposed subspace V prime of a vector space V help with anonymity and speed of proving a statement that could be extended to V? It helps with the speed, right? Not always. So it depends on the structure of the decomposition. So this is why we said, like, oh, if it takes n squared operations to check whether something lies in V, then in some sense we have some savings if we can decompose it recursively into V prime and V prime prime that are slightly more structured. But there are many decompositions that are silly that actually will not help you out. So the point is, yes, that you can think about it as, if it happens to be the case that the individual smaller vector spaces are easier to check inclusion into, then we know that like this recursive decomposition will save us work at every step. And so that's the high level idea. Okay, so hopefully that answers the question. But back to the protocol. So stare at this slide for a second and convince yourself that this protocol does work, right? And the easiest way to do it is start from the bottom and go back up. So start from 2 and 3 and then go back to 1, right? Okay, so I'll let everybody do that as a bit of a side exercise for fun. This is not going to be a homework problem, but okay. So now finally we can get to the subspace distance check. Unfortunately, this is even more complicated, which is a bit annoying than the previous one. But other than that, it's not too hard. It's just there's one more set of moving parts, which is we have to define what distance to a subspace means. And specifically, we're going to have one more definition around the distance of a matrix to a subspace. Okay, so what is the problem with the previous protocol? The previous protocol is very nice, right? It tells us something very clean, which is with some probability, we actually belong exactly into a vector subspace. But the problem is of the construction, right? When we say something like you need to check that x equals t1y plus t2z, that's an exact equality. So every entry of x has to actually be equal to the entries of t1y plus t2z, right? And so that's fine under the coding model or something like that, where it's easy to check exact equality. But it's less fine under kind of a different model, which is the direct access model, right? And this is from homework 2, which is yet to be released, but hopefully it'll be released soon, is we know that checking exact equality actually takes roughly the same amount of time as just reading the entire vector, right? And again, if that vector is very large, then that doesn't give us any savings in terms of trying to prove something in a cheaper way than it would be to just show the statement directly. So not only does the previous protocol require this notion of exact equality, which we would like to relax to kind of something that's close enough, it also requires a notion of exact inclusion. So when we say like, oh, y and z belong to this vector subspace V prime, we're actually talking about a notion of exact inclusion, like y and v must belong to this vector subspace. But from the same reason as before, it's actually not possible without significant kind of cost to check that it holds exactly. So what we want to check instead is something like y and z are close enough for all intents and purposes to the subspace that we don't actually care, right? That we don't care that they're not exactly equal to. They could be, they could not be, but they're close enough so that the proof that we want to talk about actually makes sense. Okay. So from before, all this stuff is hard to achieve unless we are explicitly in the coding model. And in general, we will not always be in the coding model. So we want to relax that to work in the direct access model. And this is true, as I mentioned before, for the exact same reason as the zero check. Okay. So as I mentioned, how can we relax these conditions, right? So from before, we can relax the notion of exact equality to something being close enough. And, we can relax exact inclusion to also being something that's close enough. And here's what this actually means mathematically. So from before, from lecture 2, the distance between two vectors will be defined as x minus y, as the number of non-zero entries of x minus y. Right. So this is, in other words, the norm of x minus y. And the reason why is because this is the same thing as saying how many entries of x differ from the entries of y. And this is going to be this thing, checking if this is not too large, is actually pretty easy to do already. And this is done via the sparsity check. And for that, see homework 2, which is, again, not released yet, but will be released soon. So the point is this idea that like two vectors are close together is actually very easy to do in the direct access model with very few queries. So that's an efficient thing we can do, and that's cool. The other thing that we need to define is the distance of a vector to a subspace. Okay, so again, from here, we have a subspace V, and we're going to define the distance of x to that subspace, which we're going to write x minus V, the norm of x minus V, as the minimum over all possible vectors in that subspace, and the distance between x and any one of those vectors. So it's the minimum of all of the possible vectors. It's like what's the closest element in V to kind of x in this like notion of distance, right? Okay. So we need one more definition, which is the notion of a matrix distance, which is given a matrix X, we're going to say that X is, within, is Q close to V, or the distance between X, which is a matrix, right? Matrix is composed of columns of vectors, and a vector space V. The distance of those two things is less than or equal to Q if there exists a matrix Y whose columns, every column is in the vector space V, such that X minus Y has at most Q non-zero rows. Sorry, this is the definition, and unfortunately, it is a bit of a pain in the ass. So it's worth parsing super carefully. I'm going to give a kind of pictorial version of this, but the point is, what does the picture look like? Okay, I want to, your claim is that the distance between some matrix X and some vector space V is, at most Q. What does that mean? Okay, I have a matrix. This matrix is going to be an n by 2 matrix in this case, right? And it's going to be called X. Great. And, to prove that you have, that X is distance, no more than Q from V, as, to prove that little inequality thing, definition above, what you need to furnish is a matrix Y, which has the property that the vectors, the columns in Y, belong in the vector space, right? So we have our X, we have our Y, whose columns belong in the vector space. And then we ask, okay, how many rows differ between X and Y? So what does it mean for a row to differ? Well, it means that, if you look at the first kind of little red box with squiggles on it, right? It means that specifically here, the second column of X differs in that entry from the second column of Y. And so that means that entire row, right, is different. So just a single change in one of the entries of that row from Y will deem the entire row to be different. Okay. And similarly, it's not double counted. So if both rows differ, so if the last entry of both columns of X differ from the same of Y, then that entire row again is counted out. It's just counted once. So any error on any entry of the row will count as one kind of error, right? And even if that row has many errors, so there's many places where those rows differ, that whole thing is just going to be counted as a single error. And so in this case, even though we have 3 places where X and Y differ, they only differ by 2 rows. So Q here equals 2. Okay. Does anyone have any questions on that? This is kind of a weird concept, but okay, cool. So let's revise the original protocol that we talked about, right? We start in the original protocol, we started with some X, we decomposed it into Y and Z along with these matrices. And then we went down and checked that Y and Z are close, are in the vector space, right? And then doing that will imply that the original X was in the respective vector space that we cared about. So let's start with a simple revision. Let's just relax all of the equal signs to distances. Okay. So this is essentially, okay, first let's check that X is close to T1Y plus T2Z. That's fine. That's just, that we can do. That's easy to check. And then we're going to draw a random R, and then we're going to take a random linear combination of Y and Z. And then we're going to check that that linear combination is close to V prime, which is the subspace that we cared about. And the next question is, of course, does this guarantee that X itself was close to V, right? And close to here is we're going to define it as some constant times, the Q's. So in this case, we've defined Q. We've said Q is an acceptable distance for X to B from, the vector space or a constant times Q. At the very last line, what we're saying is, okay, for that Q, is there some constant, 2 or 3 or 4 or something, such that X is, if we check that each of the things, satisfies those claims, X is within, a factor of 3 or 4 or something of Q, where Q is an acceptable distance for us to be happy with. Okay. So the trick, and this is a little bit annoying, is that, in fact, this is not necessarily true. So just because you check that X, is close to T1Y plus T2Z, and you check that Y and Z are individually, but yeah, sorry. Please be sure to put your question in chat as opposed to requesting video. But so if you check that, that X is close to T1Y plus T2Z, and you separately check that Y and Z are close to a vector space, it does not necessarily guarantee that X is itself close to a vector space, right? You can imagine that, there is some single entry of Y and Z, such that if you change it, that would actually change X by a lot, right? We've made no assumptions whatsoever about how T1 and T2 interact with the individual vector spaces, except insofar as we say, they are reasonable mappings. So this notion of the TIs depends on the structure of the vector space, right? So had the distance, if Y, what we need to guarantee essentially from this previous thing is that if Y and Z are close to V, then necessarily T1Y plus T2Z must also be close to V itself. There we go. So that this is a requirement that we have. It is not necessarily true of all matrices. And indeed, I think in the homework, I'm going to probably put an exercise where I'm going to ask you to construct T1 and T2 such that a single error will actually cause you to be very, very far away from the vector space. Okay, so to do that, we need to specify one more thing on T1 and T2, which is that they are basis aligned. And here's the definition. It's a bit silly because it kind of, it's exactly the definition you need to make this work, but which is we have so Y and Z here are is a matrix, and Y and Z have less than Q non-zero rows, right? This is the same thing that I was mentioning before, which is having a single entry of a row be non-zero. Will imply that the whole row is going to be marked as a non-zero row. Okay, so if Y and Z has less than a Q non-zero rows, then T1Y plus T2Z has less than or equal to Q non-zero, Q prime non-zero entries. Okay, so in some sense, if Q and Q prime are close, then the idea here is that this mapping actually preserves the distances that we care about between the vector space and the little vector spaces and the big vector space. Okay, so here's a special case, which I will assign, is if T1 and T2 are diagonal, then Q equals Q prime, right? And so these are bases aligned with this very nice property that the number of errors of the big matrix actually corresponds exactly to the number of errors in this vector after kind of applying these transformations. Okay, so at a high level, sorry, it's okay if this particular definition doesn't make much sense. It'll make sense once you start working with it. But a notion of basis alignment means that if y and z are q close to v prime, then t1y plus t2z, which is like, that definition that we gave before, is also q prime close to v. And this is the last step that we need to kind of talk about phi. Okay, so does the last statement go back to v equals v prime? It does not, right? Because v and v prime are different subspaces, right? V is the big, yes. So yeah, if it's the case that v equals v prime plus dv prime, then yes, it is true that you could like reconstruct that from the original. And we're going to see an exact example of this, which is actually phi. So, okay. So if you remember it, like, well, here, I'll say it in a second. Okay. So here's one step of the phi protocol is we're going to start with v. And the question is going to be, fundamentally the protocol wants to check, okay, there's an element belonging to v. In other words, is an element, we're given some x. And the question is we want to check if x is close to v. So what does that mean in this case of, when v is a set of Reed-Solomon codes of degree less than or equal to 2 to the k? That is a question of, does x belong, is x a vector of evaluations of a polynomial of degree at most 2k? Right, that's exactly what phi is. That's the high-level idea. And from what we know before, from the recursive decomposition step that we had, right, we have this thing of like, okay, if v are the Reed-Solomon codes, right, then we know that v recursively decomposes into a v prime, right, of degree that's half of the degree of the original, right? It's the set of even powers, so to speak, of the polynomial. Okay. So from before, we made the relaxation of the protocol originally, which is that we're going to check first that, so we're going to be given an x, and then we're going to be given a y and a z. The claim now is that x decomposes into y and z, and each of y and z are close to the vector subspace v prime. Okay. And if we know that that's true, then necessarily x itself must have been close to the original vector space v, which is, in other words, x is the evaluation of a low degree polynomial, right? Which is exactly the phi check. Okay. So the protocol again says, okay, let's check that x is close to, this decomposition, and then let's check that each of the elements in this decomposition are close to the smaller vector space v, right? Which again, it's easier to check because this is a smaller set of smaller degree, right? So it's a polynomial of smaller degree, and the evaluations are easier to check because you need less of them, so to speak. Okay, so how do we actually achieve this kind of easily? Well, the first thing is a sparsity check from what we discussed previously in the homework. And the third thing is a subspace distance check, which we know can be achieved, in this case, not from the homework, but from the paper. And so if you kind of, add the two things together, right, by triangle inequality, we know that x minus v is less than or equal to 2q, right? So if both of if the bottom statement is true and the top statement is true, then necessarily, x itself must have been close to v. And the constant that we have in front of like what close means is a factor of 2. So again, if each of the two things is q close to each other, then the final, originally x itself must have been 2q close to the original vector space, right? Okay, so from before, we have this funny thing where it's like, okay, like at the end of the day, this is phi, right? Like this is just like one step of phi. We also have this thing where like this vector space v prime is also another set of Reed-Solomon codes of some degree, right? And so certainly it also decomposes in the same way that the original vector space decomposes. So instead of checking the last step that we have in this particular, protocol, which is, we need to check that this linear combination of y and z are close to v prime, it suffices to simply kind of evaluate create a new vector, right? And then run the same protocol again, right? All we're doing is we're replacing x, which is the, a thing that we want to check is close to another subspace. We're replacing it with, another vector, which is and whatever, in this case w, and it's in v prime. So we want to check that w is close to v prime instead of checking that x is close to v, right? So we can apply the same procedure again and recursively in order to get the same result. Okay, and at some point, down the line, we're going to get a claim that's so small that it's worth just checking directly as opposed to trying to use like yet another kind of one of these steps. Okay, And so if we repeat this k times, right, with your appropriately chosen, elements and things like that, you actually get something like, at the end of the day, we've started with this x, we decompose it into y and z, and then we said, okay, now we need to check that y and z are in some vector space v prime. But instead, we can just check that like some other vector, is the new vector, which we're going to call w, is also in v, is close to v prime. But we know how to do that. I mean, that's the same check that we applied for x, except we're just going to apply it over w. And then we do it again. And then we do it again, and then we do it again, and so on and so forth, until kind of we get to some point where the last claim is so easy to check that you might as well just check it directly. Unfortunately, the details for exactly how one gets the sum to be close to, how you get this 2q and how you like show that there actually is a significant saving in total amount of like checks that you have to do, is a bit messy. It requires telescoping series and crap like that, which is, it's not complicated and it's not hard. It's just like there's like a certain accounting that has to go on that's very hard to explain verbally. So this one I will not assign as a homework because it's just like, it's not that instructive. It's simply kind of mechanical. And so, but for that, if you're interested, I would recommend you check the paper, section 4.2. Okay, so at a high level result, again, what do? We started with checking that some vector is close to a vector space V. And we reduce it to the following simpler check, which is that we have two vectors, y and z, that have two properties. First, this like t1 y plus t2z, so this recursive decomposition property holds. In other words, x is close to this recursive, decomposition, like linear or combination. And second, that y and z are themselves each close to v prime. Of course, we know from the vector subspace check that gr1y plus gr2z, right? If that is close to v prime, then that means that each of y and z must have also been close to v prime, right? That's this is just like the one of the checks that we stated, and it's also in the paper, right? And so in some sense, we've reduced kind of checking two things are close to v prime to checking that a single thing is now close to v prime. And of course, we then iterate because now we need to check that a single vector is close to v prime. Well, we know how to do that. If v prime decomposes into v prime prime, or two matrices over v prime prime, then we can apply exactly the same procedure again, one more time to do it. To check that this w, or this gr1 y plus gr2z are close to v prime. We can just apply the same procedure that we did over x, except for the new vector space. And doing this recursively, you could imagine if you get a constant amount of savings for each round that you do this, then at the end of the day, you get an exponential amount of savings in the number of times you repeat the procedure. And that's exactly what Phi does, and that's how it actually achieves succinctness. So at a high level as well, we have no notion of polynomials. Polynomials aren't really needed in this discussion. Polynomials only enter in the fact that like it is a concrete set, a concrete vector subspace, which has this kind of recursive decomposition. But they do make a great practical case, right? Like it turns out that they have just the right properties to have this notion of basis alignment. They have just the right properties to have this, the checks at the end be a little bit easier at every step, and so on and so forth. But the point is, polynomials themselves are not exactly kind of the most necessary aspect of this. There might be other structured codes that are also similarly useful, which could lead to kind of more interesting or perhaps more efficient similar kind of constructions. Okay, and there's a question here, which is the iteration deterministic then? I'm not sure what the iteration deterministic is. Every step of the iteration has a random component. The number of iterations could be deterministic indeed. Yeah, so that depends on the protocol and depends on what you're interested in doing with it. But generally, the answer is yes. So the number of times that you recursively decompose this thing should, in general, be deterministic. Okay. So anyway, quickly conclusion, we're kind of reaching up on time, is we have finished the course. So congratulations for making it all the way through. The course, began probably simple and kind of, nice. And then, unfortunately, to say real things, there are details to it. And so you have to chew a little bit of glass. And so, but, the interesting part is that, look, we covered a bunch of tools, right, that are very general. They depend on kind of no real structure for a lot of things. And they generalize things that we know and love from the ZK literature. And with those tools, we gave an example of one application. So here specifically is how to understand Fry from a linear algebraic perspective. And that's kind of all you need. Like linear algebra is all you need if you want to make the meme. But the point is that there's likely many more, right? Like Fry is almost incidental. It was one of just simply a thing that we were curious about proving, again, a weak notion of security of it. And we ended up doing it. And so it's cool. Here's what we're presenting. And you can understand it from a pure perspective of linear algebra. But there's a question, are there more things that you can understand in this sense? And so one thing that I encourage you to do is there are many proofs out there in literature that can be rewritten using this type of framework. Not all of them, and indeed there's many that are not, right? But there's a few that actually might be like quite interesting to sit down and be like, okay, how do we write this proof, which probably has a bunch of lemmas and all of them play together in different parts? How do we write this proof, in terms of this probabilistic implication language, for example? Or can we rephrase this proof, which is in terms of polynomials, in terms of just purely kind of error correcting codes? And that would give us a general version of it. And so on and so forth. So, but the point is, okay, so at a high level, it's kind of a nice framework to think about stuff, and it seems to be applicable in many cases. One of the natural questions that you have is how many more cases? And so that will be an exercise for the reader. Not because I know the answers, simply because I'm just curious if anyone has any ideas. More broadly, so if you saw an error on the slides, or you see an error in the homework, or you have solutions for the homework, please do a pull request on the GitHub repository. The GitHub repository should be up on the Discord in one of the pinned links. And if you have slide feedback as well. So if something isn't clear, or you think you can maybe rewrite it in a better way or something like that, please feel free. If you want to, tech up some of my crappy hand drawings, feel free to do that too. I'm happy to take pull requests and things like that. And none of this, of course, is possible without everyone's help. Thank you so much for attending. Thank you, Anna and Gaylord, so much for having me here. Cool. Anyways, thanks. I'll be taking questions now. So here, I'm gonna
yeah, there is one question actually, so I'll let you go through
in here. Okay. So question, does reducing the number of errors in a row to 1 for the matrix instance reduce the security of the protocol? I'm not sure I fully understand what it means to 1 for the matrix instance. Sorry, unfortunately,
I'm not sure either. So either you can jump in and answer, or maybe reformulate for us to read. While you're deciding on that, yes, I wanted Anna to jump on. Go ahead.
Hi, Anna.
This question, does reducing the number of errors in a row to 1 for the matrix instance reduce the security? So it's reducing the number of errors to 1.
It does not actually change the security of the protocol as stated here, I guess. I'm not sure I fully understand. I'm going to map it to something that I think I get. But essentially, like, having 1 or many errors in a row will actually make no difference to you. And the main reason why is because you're kind of taking a linear combination of all of these things. So if any one of the entries is screwed up, then you have this like nice thing of like the whole, that entry after taking a linear combination will probably also be screwed up. So that's the idea.
Next question. What if we find a typo in the paper? How's the best way to let you know?
Feel free to email me, ping me in the Discord. There are actually, funnily enough, this is why I encourage you to read the GitHub version, not the ePrint version. So the GitHub version has, unfortunately I don't have the paper up on GitHub, but the EPUB version, the version that I have on my website is actually up to date and has less errors than the ePrint one, which I will update at some point, but I have not yet.
Yeah, Chinonso, I don't know if that answered your question earlier, but if you want to make some precisions, now is the time. If you want to unmute yourself. Yeah, no.
Unless you didn't mean to jump up with us.
Maybe, yeah, I don't know.
Okay,
cool.
I guess we can. So, yeah, I think if this is the end of our session, I want to say a big thank you, Guillermo, for doing this like short ZK Hack study group with us. This was the ZK study group mini. We were kind of trying out this new format. How did you find it?
Me or?
Yeah, how did you find it? Oh, yeah.
Oh, yeah. Actually, I don't think it is. Maybe that was hard. Oh, there we go. Yeah.
Okay.
I was like, wait, does this work?
Oh, cool.
Okay. Anyway, so I thought it was good. I don't know. It's nice to have a short set of sessions that's contained. Unfortunately, things have been a little crazy, so I apologize about the last minute slides and homework, but hopefully they made sense. I have no idea if they did. That would be very curious to have feedback on that. And again, if you have concerns, conditions, comments, please PR or just send those to me on Discord. But hopefully it was good. I don't know. I'm actually curious for everyone else's feedback on it.
Totally. Yeah. I mean, and I think we're going to ask this in our chat, but we're really curious from the audience what you guys thought of this kind of thing, this sort of short form study groups. Also, we're using right now this Ring Central Hopin. Like Hopin was the tool we used to use, and now it's been bought by another company. I am wondering if people like it, because we're thinking of running ZK online on this again, which we've done in the past, but we wanted to know if it worked out. I liked it. I don't know. It seems like it's still working pretty well. But yeah, thank you so much, Guillermo, for taking the time and spending these 2 weeks with us.
Well, thank you both for having me.
We're going to be releasing this video on the YouTube channel. Actually, it might be good, Guillermo, to just monitor that YouTube channel too, to make sure that, because there's sometimes people might actually ask questions on the YouTube videos themselves. And we're going to keep this chat open on the Discord for a little while, I think, as people watch the videos kind of after the fact. Yeah. And I know actually, yeah, we had been talking, Gaylord and I had been talking just today, I think, about potentially creating a little resource with all of these videos potentially in the new year. So, yeah.
Yeah, it's actually not the end, because there is a bunch of homeworks that I think people are going to wait for as well. But yeah, typically having the homeworks and maybe some links to the GitHub with beginning of solutions or even final solutions would be a great resource for future students. So yeah, looking forward to that.
Yeah. Sorry, apologies about not releasing the homework. I
think it's fine. I'm not even sure so many people actually done the one from the first session.
Yeah.
So this is fine, I feel like, for the time. But yeah, definitely we'll be looking for to it in the next few days and weeks. Yeah.
Yeah, I think of this. I mean, I don't know how you feel, Guillermo, but I feel like this is a nice kind of companion to the paper.
It's very nice. I mean, it's great.
So when we have this in one place, it might be cool to share it once again, just sort of like, here's the paper, here's a video series that goes through the paper, here's a bunch of exercises you can do. And I hope
it's funny, because actually a lot of them were based on questions that I had from people about certain parts of the paper, where they're like, I don't know how to do this proof. And it's like, okay, homework problem, part one actually is exactly that. It's you should work it out. It's just sometimes it's easier to do these things when you do them with pen and paper than it is for someone to just tell you what it is. But anyways, thank you again. It's kind of fun. It's a weird format. I've never done this for any paper before. I've given lectures on it, but never with homeworks on a specific paper. But
in a mini version, the 3-parter seemed like a good fit.
Exactly. So it's kind of fun. Anyway, so thank you. It's definitely entertaining. I'm curious to see what people think.
Very cool. All right. Thanks everyone for coming out, for the wonderful questions. Mahmoud, you had great questions this time. Thank you so much for that.
Thank you all.
Yeah. And I guess we will see you, I think, in the new year, like in terms of a format like this. I don't know if you all know this. I'm just going to do a little plug for ZK Hack Online. So we do our hackathons. Those are kind of, weekend-long hackathons. But the ZK Hack Online event, this is a 4-week workshop online, like in a platform like this, with a puzzle hacking competition. And this is going to be running from January 16th until February 6th. We're going to be making a bit more noise in the Discord about that. I don't know if people have been to the previous 3. This is our 4th time running this online series, but it'll be a lot of fun. So we'll see you in the new year for that. Okay, cool.
Thanks, everybody. Thanks, Guillermo.
Have a good one.